sometimes they will have lower like this. Okay, and you're plotting. What you're plotting here is the electron density. Remember, in quantum mechanics, wave function doesn't mean anything. It's just a mathematical treatment to lead you to generate these probability. And probability means something. It equivalent to the current. It's a charge. The likelihood of finding the charge in that space. That's what psi squared means, the probability. So-called wave function density. Sometimes called electron density that you see. So that's the physical measurement that you can actually see. And the Abel theory emphasizes, right, why chemists love it so much is because it gives us a handle on understanding interaction between different atoms. Because it emphasizes the delocalized nature of the electron density. You see, here you have a tightly bound thing, and this is delocalized between them. This whole thing, this electron is moving about in a much bigger space. Happier, and that's what, and it can roam around in more space, creating a lower energy state. That's why it's lower like this. Okay, so delocalization leads to lower energy, and it's extending, it's sharing between atomic centers. That's why we have to call them molecular orbital instead of just atomic orbital. It's sharing within the entire molecule that we have. And now, what should we do? Well, once we got diatomic, a simple one, both homogeneous diatomic, this two are the same, or heterogeneous AB, this is just AA type structure, you have AB type structure. Now, if we start adding atoms to this diatomic, we have more and more atoms. Let's say a cluster triatomic, let's say linear cluster. And what should we have? Well, because we start off with 2 AO, we should have 2 MO. If we start off with 3, we should have 3 MO. So it accumulates. It's just adding more and more system. You should the number of energy level is conserved as you add them up together. And we now have a solid with a very large number of atoms, and the separation between this energy level become smaller and smaller, and these origin, the original bonding, anti-bonding orbital, as in my hydrogen molecule, now evolve into valence and conduction band solid. Okay, and the separation between them, between energy gaps. So here's a rough diagram of how we should think about this. So initially, in here we have 1 atom, so we just have 1 happy, that's my hydrogen atom. And now if you put 2 together, 1 hydrogen atom next to another hydrogen atom like this, this is our picture, you generate the MO, right? You have 1 sigma orbital, 1 sigma star orbital, right? And you fill them 2 electrons in here. Now you have more and more, what will happen? This is starting to add up, right? You're starting to split more and more, depending on how you combine your atomic orbital. You have these things. And eventually, it's so dense that, that you have to draw as just a hatch line like this. But in reality, you have many energy states in here. They're not continuous. So even though I draw it like this, it does not mean that they're continuous. They're still discrete energy state. They all have its own separate energy. So in order to avoid confusion, right? So you can see this is not very ideal. You know, when you draw a picture like this, it's not so ideal. So people say, well, maybe we should draw the density of state because they are so dense in this direction in a certain volume. So you plot them. So for example, at this energy, right? At this energy, you counted how many energy level you have here. So what is density state? So here I say at this energy, let's say I found 2 or 3. So you plot 2 or 3 in here. If I go lower, I got 1 only in this region. So you plot 1 down here, right? So you can plot the amount, the number of energy level that you have within a certain E plus delta E region, right? And then you can some way, the density state is a degeneracy. You can think of it, it's kind of like degeneracy at that energy. How many orbitals are available at that particular energy, right, per volume? That's the so-called density of the states. Okay? So instead of plotting a level like this, I have to plot a curve like this, and this tell me the number of orbitals at that particular energy that I have. Okay? And so when you see the electronic band structure, they are plotting the density of state here, and this is energy for one particular k direction, right? For particular k direction, because you have to look in a certain direction. If you look in a different way, they will have a different density states.
Does it mean it has different electronic structure or different crystallographic structure in different, like along K and then along other directions?
Okay, so the question is that does it mean that it has different physical structure in different directions? Yes, the answer is in fact that's why you have different electronic band structure. It's due to, in fact, the periodicity. Right? Remember we talked about Brillouin zone. If you look at different direction in the Brillouin zone, it corresponds to different direction in the physical space. And in this different direction in the physical space, the periodicity is different along different line of sight that you look. Okay, so that's why different direction generate different band structure, different density states, right, along that particular direction. So you can see, so it's a very complicated plot. People may get confused at this point because here I'm plotting energy, right? So the y-axis is energy, and the x-axis, I'm sort of inverting my curve, right? Turning my curve 90 degrees. I'm plotting the number of orbital energy level for that energy, and I make a point, and this I make another point, and so forth. And I'm drawing this, the number correspond to the energy level that I found at this particular energy, right? So that is known as a band structure. And this corresponds only to one K point, okay, one residual space point. And then now imagine you have to do multiple K points, right? So that is getting more and more confusing as you do that, okay? And that's why people have a tough time initially to understand these pictures. But really, they are like this. They are nothing more than this for one particular direction that you look. Okay, so the MO will not be distributed evenly in different crystallographic axes over all energy, right? So this is exactly how the physical structure relates to the electronic structure. This is why we talk about physical structure first. This is how it's connected. We think of this as a form of degeneracy corresponding to how you combine the AO together to make different type and symmetry of this. And this leads to density state, which is defined this way. If you integrate, so this is NE. If you integrate dE, so how do you think about it, right? I take a slight off, right? And this is E, and this is E plus dE, right? Very tiny slight. This region is dE, like this, right? And this number, if I combine it together, is correspond to number allowed energy level per volume. This is why it's called density. You have to think about per the amount of material you have. This is why you have to say per volume. Clearly, you cannot say just arbitrary because it has to scale with the amount of material you have. And this is how you scale it per unit volume of the solid in this energy range, E plus dE, like that. And that gives you, let's say, in this energy range, I have 10, and then I come down here and I found 2 or something like that. So this is how you plot it out in this. So, and the density state time dE is the number of energy level, in fact, in a certain range per unit volume. That's what density state is. Okay. Now, from this, I think I will do a couple of aside, if you like. So first of all, you have optical properties, right? So just mention briefly optical property of metal insulator semiconductor, because we just introduced this concept of density state. We can think about and band gap, right? Band gap, and so we are thinking about absorption of light, absorption and reflection of light. And when we talk about optical property, the word opticals, usually people think associated with the word optical, associated with optical property in the visible range, the range that our eye can see. You know, our eye can be sensitive to the visible spectrum of the electromagnetic spectrum. Whereas of course there are other regions in the electromagnetic spectrum, like ultraviolet and infrared, that we cannot see, our eye cannot see. Okay, so usually we intend to think in terms of visible. That's what's implied. So so forget about this. What I wrote on top here. We have